Somewhere 13 billion light years away, there's an object that shouldn't exist. The quasar is so massive that its black hole weighs as much as 800 million of our suns, and it came into existence just 700 million years after the Big Bang. It's impossible. The universe simply did not have time to create something like this. And yet it is there, challenging every theory, every calculation, every equation. The cosmos is full of such mysteries, as if someone deliberately left clues that we do not understand something, that our physics works only in a narrow corridor of reality, and beyond it, something completely different begins. Take the Great Attractor. This is a gravitational anomaly hidden behind the plane of our galaxy, where the Milky Way rushes along with thousands of other galaxies. We are moving towards it at a speed of more than 2 million kilometers per hour, but we cannot really see it. Dense clouds of dust and stars from our own galaxy block the view. We are hurtling towards something invisible, attracted by a force we can barely measure. Every galaxy within a radius of 600 million light years obeys this attraction. What is this? A supercluster of galaxies? Or something even stranger? But even the Great Attractor turns out to be only part of an even grander structure. Recently, astronomers discovered something more. Laniakea, a supercluster of galaxies 500 million light years across. Our home. But Laniakea is also flowing to something even bigger, to Shapley, a supercluster so gigantic that it contains a mass of tens of thousands of galaxies the size of the Milky Way. The universe flows. Vast cosmic rivers from galaxies flow through invisible channels, outlining a structure that is too large to be embraced by intelligence. And there are voids between these rivers. Voids. Regions of space are almost devoid of matter, stretching for hundreds of millions of light years. Some are so huge that it takes 300 million years for light to cross them. There is practically nothing inside. The vacuum of space within a vacuum. If our civilization originated there, we would see a virtually empty sky and would never know that the universe is full of galaxies. Cold spot. In the cosmic microwave background, the cosmic microwave background radiation from the Big Bang itself. There is a region the size of 1,000 moons in our sky that is colder than it should be. 70 microkelvin colder than average. This may seem like a negligible difference, but on the scale of the entire universe, it is a screaming anomaly. One explanation is that there is a super void, a giant void through which radiation loses energy. But even the largest void cannot fully explain this coldness. There are also more exotic theories. Is this a trace of a collision between our universe and another universe in the first moments after the Big Bang? A scar from an encounter with a parallel reality, dark stream. In 2008, astronomers discovered that hundreds of clusters of galaxies were moving in the same direction at a speed of about 3 million kilometers per hour, ignoring the entire surrounding structure of the universe. They flow to a single point at the edge of the observable cosmos, as if they're being pulled by something beyond anything we can see. What's there? Beyond the event horizon of our universe? Some suggest giant structures beyond the observable cosmos. Others talk about traces of a previous universe that existed before the Big Bang. And then there's the Boötes hole, a void with a diameter of 330 million light years with practically no galaxies. In the area where 2,000 galaxies should be located, there are only 60 of them. What could have created such a void? How did matter escape this region? It was as if someone had carved a piece out of the fabric of space. But if we talk about things that don't make sense, we can't help but mention dark energy. 70% of everything that exists is a force that tears the universe apart. It causes space to expand with acceleration. The larger the universe, the faster it grows. Galaxies are moving away from each other faster and faster. In 150 billion years, any galaxy outside our local cluster will have disappeared beyond the event horizon. Future civilizations will see only a small island of galaxies in endless darkness and decide that this is the entire universe. They will never know about the Big Bang because the CMB radiation will stretch to infinity. All information about the origin of the cosmos will be lost. But what is dark energy? We don't know. Absolutely. This is the most honest admission of failure in the history of science. 70% of the universe is a question mark, and another 25% is dark matter, an invisible substance that does not interact with light, but curves space with its gravity. We see the galaxies spinning too fast. They should have been torn apart by centrifugal force, but something invisible is holding them together. We see gravitational lenses. The light of distant galaxies is bent around massive objects, but where there is a curvature, we don't see enough ordinary matter. There is something, but it is transparent to the entire spectrum of electromagnetic radiation. Bullet galaxy. Two galaxy clusters collided, and when astronomers studied the debris, they found that most of the mass passed through the collision without slowing down, while ordinary matter, gas and dust, remained in the center, heated to millions of degrees. Dark matter passed like a ghost through a wall. This was the first direct proof of its existence. But we still don't know what it consists of. WIMP? Axions? Sterile neutrinos? Primordial black holes? Every laboratory on Earth is looking for it, but so far there is silence. Only 5% of the universe is what we understand. Atoms, light, planets, stars, you, me. Everything else is terra incognita. And this is where it gets really strange. Because there are objects that challenge not just our theories, but the very logic of existence. Magnetars. Neutron stars with a magnetic field a quadrillion times stronger than the Earth's. So powerful that it warps the shape of atoms, turning the vacuum around the star into something like a solid medium. If the magnetar were halfway to the moon, it would erase all the information on every credit card on Earth. He would literally pull the iron out of your blood. And at a distance of 1,000 kilometers, the magnetic field would tear you into atoms. These stars sometimes experience starquakes. Their crust cracks, releasing more energy in a fraction of a second than the sun radiates in 100,000 years. In 2004, the outburst of the magnetar SJAR 1806-20, located 50,000 light-years away, momentarily changed the shape of the Earth's ionosphere. The brightest event ever recorded from an object outside the solar system. Hypervelocity stars. Stars that move so fast that they leave the galaxy. 3 million kilometers per hour. What can accelerate an entire star to such a speed? The supermassive black hole at the center of the galaxy can do this if the star gets too close in a binary system. One star is captured. The second is shot into space as if from a sling. These exiles are doomed to drift forever in the intergalactic void. In billions of years, when their fuel runs out, they will be extinguished in absolute solitude, trillions of kilometers from the nearest galaxy. Strange radio signals from space. Fast radio bursts are FRBs, pulses of radio waves that last milliseconds, but carry as much energy as the sun emits in an entire day. They come from distant galaxies, billions of light years away. What can produce such a powerful pulse in a thousandth of a second? We don't know. Some are repeated with mathematical precision every 16 days. FRB 121,102 emitted hundreds of pulses, and astronomers traced it to a dwarf galaxy 3 billion light years away. There, in the region of active star formation, something is sending these signals. Magnetar? An exotic pulsar? Or something we haven't even thought about? Tabby is a star, KIC 8462852, a star that dims in an unpredictable way. Sometimes its brightness drops by 22%. No planet can block that much light. Even Jupiter would only block 1%. The original hypothesis was so audacious that most astronomers were reluctant to say it out loud. The megastructure of an alien civilization, Dyson's sphere. But further observations showed something no less strange: dust. A huge cloud of dust of unknown origin. From where? A ruined planet? A swarm of comets? The mystery remains. What about Oumuamua, the first interstellar object ever discovered in the solar system? Cigar-shaped, 400 meters long, rotating every 8 hours. He moved strangely. It accelerated, leaving the solar system, as if something was pushing him. Comets accelerate due to the release of gas, but Oumuamua showed no signs of degassing. No tal, no coma, just a dark, elongated object that changed speed for no apparent reason. One Harvard astronomer, Avi Loeb, suggested that it could be a solar sail, the technology of an alien civilization. Most of his colleagues rejected the idea, preferring explanations like hydrogen ice. But the truth is, we don't know. Oumuamua is gone, and we'll never be able to catch up with him to study him closer. Space isn't just weird. He systematically violates our expectations. Every time we think we have understood the rules, the universe shows us an exception so egregious that we have to rewrite the textbooks. Take black holes. We thought we understood them. Massive stars collapse, creating a singularity, a point of infinite density surrounded by an event horizon beyond which nothing can return. Even light. Simple, elegant concept. But then we started to find them. And it turns out that the universe is producing black holes of size that shouldn't exist. 618, a quasar powered by a black hole with a mass of 66 billion solar masses. Its event horizon has a diameter of almost 2,000 astronomical units, 40 times the orbit of Neptune. If this black hole were to replace our sun, its horizon would swallow everything up to the Oort cloud. It's so massive that it doesn't fit into any model of black hole growth. The universe simply did not have time to raise such a monster. Even if this black hole had been devouring matter at the highest possible rate every second since the Big Bang, it shouldn't have reached that size. And this is not the only one. Phoenix A, with a mass of 100 billion suns. Home 15A, 40 billion. IC 1101 at its center contains a black hole that could weigh more than 100 billion solar masses, although estimates vary. These objects challenge every accretion model, every formation theory. They're too big, too old, too massive for the universe of their age. And then there is the opposite problem: primordial black holes. Theoretical objects that could have formed in the first fractions of a second after the Big Bang from density fluctuations. They could be of any size, from the mass of a mountain to the mass of a planet, sealed in an event horizon the size of an atom. If they exist, Billions of them fly through the solar system every year. Through the Earth. Through you. Invisible, imperceptible, almost not interacting with matter. Some scientists believe that they may be the dark matter we're looking for. Gravity without light. Mass without matter. Stephen Hawking showed that black holes are not eternal. They radiate. Hawking radiation is a quantum effect on the event horizon, where virtual particles become real and the black hole slowly loses mass. For a supermassive black hole, this process takes a time that exceeds the age of the universe by a factor of googolls. But a small primordial black hole could have evaporated over the lifetime of the cosmos. At the final moment, when all the mass is used up, it explodes with a flash of gamma radiation. We are looking for these outbreaks. They haven't found it yet, but this does not mean that they do not exist. Black holes warp time. Near the event horizon, time slows down so much that if you watch someone fall into a black hole, you'd see it slow down, turn red with gravitational displacement, and freeze millimeters from the horizon without ever crossing it. But from the point of view of the faller, he would have slipped through the horizon in seconds without feeling anything special. Two observers, two completely different realities. Both are correct. Inside a black hole, space and time switch roles. A singularity is not a place in space, but a moment in your future. As inevitable as the next second. You can't help but reach it, just as you can't stop time. All trajectories lead to it. Geodesics point in only one direction, forward in time, down into the singularity. But what happens there? General relativity predicts infinite density, infinite curvature. Physicists hate infinities. They mean that the theory has broken down, that the equations no longer work. We need quantum gravity to understand the singularity, but we don't have it. String theory, loop quantum gravity, causal dynamic triangulation all claim to be important, but none have been proven. Maybe singularities don't exist at all. Maybe quantum effects stop the collapse on the Planck scale, creating a fuzzball or Planck star, an object so dense that quantum uncertainty becomes the dominant force. Or maybe the interior of a black hole is a whole new universe expanding in its own time. Schwarzschild-Sitter's hypothesis. Each black hole is the seed of a new cosmos. If true, then our universe could be the interior of a black hole in the parent universe. The Big Bang would have been the moment when matter collapsed beyond the event horizon on the other side. The expansion of our cosmos is a collapse from the point of view of an outside observer. Time flows in different directions on different sides of the horizon. This would explain why the universe is expanding, why there is an event horizon, the edge of the observable cosmos. Why are the laws of physics so fine-tuned that they allow complex structures to exist? Natural selection at the cosmological level. Universes that produce more black holes create more daughter universes. The parameters of physics evolve to values that maximize the production of black holes. And stars, planets, and life are byproducts of this process. But this is only a hypothesis. Beautiful, but unprovable. And there are even stranger things. Wormholes, bridges in space-time that connect distant regions of space or even different points in time. Solutions to Einstein's equations show that they are mathematically possible, but a stable, traversable wormhole requires exotic matter, a substance with negative energy, something that pushes space outward instead of pulling it inward. This violates all classical energy conditions, but quantum mechanics allows for negative energy on a small scale. Casimir effect. Two metal plates in a vacuum are attracted to each other because there are fewer virtual particles between them than outside. The area between the plates has a negative energy density relative to a normal vacuum. If it were possible to amplify this effect, to accumulate enough negative energy, maybe it would be possible to stabilize the wormhole. But even if wormholes are possible, they could be deadly. Any disturbance, one particle, one photon of light, could have destroyed the tunnel, collapsing it with such force that energy would have been released that could incinerate everything within a radius of light years. And if a wormhole connected two moments in time to create a time machine, it would allow causal paradoxes. You could go back and kill your grandfather before your father was born. Hawking proposed the chronology defense hypothesis, that the laws of physics conspiratorially prevent time travel by causing the collapse of any structure that might allow it. But this is just a hypothesis. We do not know whether nature is right to defend itself. White holes, the theoretical opposite of black holes. Regions of space from which matter and light can only come out, but nothing can enter. Mathematically, they exist in Einstein's equations as a time inversion of a black hole. But we've never seen one. If they existed, they would be the brightest objects in the universe, spewing matter and energy into the surrounding cosmos. Some have suggested that the Big Bang was a white hole, a singularity that spewed out the entire universe. Others believe that white holes may be the final stage of black hole evaporation. When Hawking radiation reaches a critical point and the remnants of mass are ejected outward in a catastrophic explosion. But this is all theory. Beautiful mathematics without empirical confirmation. Naked singularities. If the black hole spins fast enough, centrifugal force can destroy the event horizon, exposing the singularity to the rest of the universe. This would violate Penrose's cosmic censorship hypothesis, the idea that nature always hides singularities behind event horizons, protecting the universe from their insane physics. A naked singularity would be a place where causality collapses, where the future is not determined by the past, where everything is possible. Information could flow out of it in unpredictable ways. This would destroy determinism. Some physicists believe that if naked singularities existed, they would make the universe unpredictable at a fundamental level, not because of quantum uncertainty, but because of classical chaos. Fortunately or unfortunately, we have never observed one. Maybe they are impossible. Maybe we just don't know where to look. The universe also produces structures so large that they defy the cosmological principle. The idea that on large scales the universe is homogeneous and isotropic. The Great Wall of Hercules Corona Borealis, a galactic filament 10 billion light years long. It is the largest known structure in the universe. It takes 10 billion years for light to travel from one end to the other. It is so large that it should not exist according to the standard cosmological model. Structures of this size could not have formed during the existence of the universe. Gravity isn't fast enough. Even if all of the dark matter worked perfectly to bring galaxies together, there wouldn't be enough time to create something so grandiose. And this is not the only structure that violates the rules. Large quasar cluster LQG, 73 quasars, spread over an area of 4 billion light-years across. Sloan Wall, giant GRB arc GRB ring. Each of these structures is too large, too organized, too structured for a universe that is only 13.8 billion years old. It was as if someone was building the scaffolding before the foundation was laid. Maybe our cosmological model is incomplete. Maybe there were processes in the early universe that we don't understand. Phase transitions, topological defects. Cosmic strings are hypothetical one-dimensional defects in space-time left over from the early cosmos. If they existed, they would be thinner than an atom, but they would contain a mass of mountain ranges for every centimeter of their length. Their gravitational field could act as seeds for galaxy formation, pulling matter together along cosmic string lines and creating the filaments of galaxies we see today. But we have never seen a cosmic string. They remain theoretical artifacts of high-energy physics. There's an even stranger possibility. What if the universe didn't start with the Big Bang? What if what we call the Big Bang was a rebound? The moment when the previous contracting universe reached its minimum size and began to expand again. Cyclic cosmology, an endless sequence of expansions and contractions. Each cycle erases most of the information about the previous one, but some traces may remain. Anomalies in the cosmic microwave background. The strange concentric circles that some astronomers claim to see are echoes of gravitational waves from cataclysmic events in the previous universe. Roger Penrose, who won the Nobel Prize for his work on black holes, proposed a conformal cyclic cosmology. In the distant future, when all the black holes have evaporated, when all the stars have gone out, when all the radiation is scattered, the universe will have lost all sense of scale. Without massive particles, there would be no way to measure time or distance. An infinitely old, infinitely large universe would become mathematically equivalent to an infinitely small, infinitely young universe. And at that moment, the transformation will take place. What looks like the heat death of our universe will be the Big Bang of the next one. The end becomes the beginning. Time closes in a loop. It sounds like science fiction, but the math works. The question is whether it corresponds to reality. And then there's the multiverse. The idea that our universe is just one of an infinite number. This follows from eternal inflation, a theory that explains the homogeneity of the cosmos. In the first fraction of a second after the Big Bang, space expanded exponentially rapidly, smoothing out any inhomogeneities. But inflation does not stop everywhere at the same time. In most regions, it goes on forever, and only in rare bubbles does it end, creating universes like ours. Each bubble is a separate cosmos with its own laws of physics, its own constants, its own fate. An infinite fractal of universes born from eternally inflating space. If this is true, then our universe is incredibly lucky. The constants of physics are tuned to many decimal places to allow the existence of atoms, stars, planets, and life. Change the strength of electromagnetism by a few percent, and atoms cannot form. Change the nuclear force, and stars can't fuse carbon. Change the cosmological constant, and a universe will either collapse in microseconds or expand so fast that galaxies will never form. We live in a very narrow corridor of opportunities. The anthropic principle explains it simply. We are observing a universe tuned to life, because in any other universe there would be no one who could ask this question. Out of an infinite number of universes with different constants, we will inevitably find ourselves in the one that allows our existence. This is not a miracle. These are statistics, but it also means that most universes are dead. Empty, expanding voids without structure, without history, without meaning. Some physicists hate the multiverse because it's impossible to test. If other universes are beyond our cosmic horizon, separated from us by eternally inflating space, we will never be able to see, measure, or touch them. Science requires testable predictions. The multiverse does not give them. It is a philosophy disguised as cosmology, critics say, but proponents answer. If the theory correctly predicts everything we can observe and logically requires the existence of unobservable regions, we must accept these consequences. We don't reject the inside of black holes just because we can't look there. If our bubble universe collided with another bubble universe in the early moments of inflation, that collision would leave an imprint on the cosmic microwave background. The disk is of a slightly different temperature, a trace of a cosmic impact. Some astronomers claim to see hints of such collisions in the data. Others say it's statistical noise, pareidolia in numbers. The debate continues. And then there's quantum mechanics, which offers its own version of a multiverse. The many worlds interpretation. Every time a quantum dimension occurs, the universe splits. All possible outcomes are realized, but in different branches of reality. An electron passes through the left slit in one universe and through the right slit in another. Both universes are equally real. Schrödinger's cat is alive in one branch and dead in another. No collapse of the wave function. No random selection. Only the infinite branching of reality at every quantum crossroads. If this is true, then there's a version of a universe for every possible location of every atom, for every possible outcome of every quantum event since the Big Bang. Infinity beyond infinity. In one branch, dinosaurs never went extinct. In the other, the Earth has never been formed. In the third, you made a different decision a second ago and are reading a different text. Every possible story is realized somewhere in the quantum multiverse. This explains why quantum mechanics is probabilistic. We can't predict which branch we'll end up in, only the probability of ending up in a particular one. Consciousness slides along the tree of reality, following one path through an endless labyrinth of possibilities. But it also means that every action we take creates copies of us living alternative lives. There's a version of you that has made every possible choice. An endless ensemble of versions, each with its own memories, its own fate. Most physicists find the many worlds interpretation elegant but extravagant. The Copenhagen interpretation is simpler. The wave function collapses when measured. But what is measurement? When exactly does collapse occur? These questions have remained unanswered for 100 years. The cosmos is also full of objects that test the limits of our instruments and our understanding. Pulsars are neutron stars that rotate hundreds of times per second, emitting narrow beams of radio waves. Some are so stable that they rival atomic clocks in accuracy. PSR J1748-2446 AD rotates 716 times per second. Imagine an object with a mass greater than the Sun, compressed into a sphere 20 kilometers in diameter, rotating so fast that its equator is moving at a quarter of the speed of light. A little faster, and the centrifugal force would tear it apart. He is at the very edge of what is physically possible. Pulsars bend the space-time around them so much that light passing nearby is delayed by microseconds. Their gravity bends light rays, creating gravitational lenses. Their magnetic fields accelerate particles to relativistic speeds, and they're incredibly dense. A teaspoon of matter from a neutron star would weigh 1 billion tons on Earth. It would burn through the planet if it somehow materialized here. But there are even more extreme objects. Quark stars are a hypothetical stage between a neutron star and a black hole. With sufficient pressure, neutrons are destroyed, and the quarks of which they are composed become free. A star turns into a blob of quark matter, a substance so dense and strange that it exists in a state that we can only recreate in laboratories for microseconds. We may have observed quark stars before, but we thought they were unusually dense neutron stars. Or maybe they are impossible, and the collapse goes directly from the neutron star to the black hole with no intermediate states. Strange stars, an even more exotic possibility. Stars made of strange matter, a form of quark matter that contains strange quarks in addition to up and down quarks. Strange matter may be more stable than ordinary nuclear matter. If this was true, then any piece of ordinary matter that touched the strange matter would instantly turn into it. A chain reaction that turns protons and neutrons into strange quarks. Strange matter could be the true ground state of matter, and everything we know, atoms, molecules, our bodies, is metastable. A single touch of strange matter could turn the Earth into a sphere of quark fluid in minutes. Fortunately, if strange matter exists and is stable, it would have to be extremely rare. We would see its effects. Cosmic rays containing strange planes, blobs of strange matter, would bombard Earth. Detectors would pick them up. So far, nothing. Either the strange matter is unstable, or it simply does not exist. But the very idea that there's a form of matter that could catalytically transform all ordinary matter is frightening. This is the ultimate gray goo, a hypothetical scenario where everything turns into a homogeneous substance. Vacuum decay is another version of this nightmare. If our vacuum is not a true ground state, but a false, metastable one, then somewhere, sometime, a quantum tunnel transition to a true vacuum may occur. A bubble of true vacuum would expand at the speed of light, transforming the physics within itself. The constants would change. Atoms would fall apart. The whole structure of matter would be rewritten, and we would never see it coming. The wall of destruction moves at the speed of light. No warning, no way to escape. One moment you exist, the next you are not, and the entire universe around you has been transformed into something fundamentally alien. This could already be happening somewhere in space. Bubbles of true vacuum could be devouring distant galaxies right now, and we won't know until billions of years later when the front reaches us. Or maybe it's impossible. Maybe our vacuum is stable. Calculations show that we are on the edge. Almost stable, but not quite. The mass of the Higgs boson and the top quark puts us in a region that physicists call metastability. The vacuum will probably outlive the age of the universe, but it is not guaranteed. There are also cosmic phenomena that we observe but cannot explain. Gamma ray bursts, the brightest electromagnetic events in the universe. In a few seconds, a single gamma ray burst releases more energy than the sun does in its entire 10 billionth lifetime. If a gamma ray burst were to occur in our galaxy and be aimed at Earth, it would sterilize half of the planet, destroying the ozone layer and flooding the surface with deadly radiation. We think that short gamma ray bursts come from the merger of neutron stars, and long ones come from the collapse of massive stars into black holes. But some gamma ray bursts don't fit into any category. Too long for mergers, too short for collapsars. What causes them? We don't know. GRB 080916C. A gamma ray burst so powerful that it could be seen with the naked eye from 12 billion light years away. If you were looking at that part of the sky at that moment, you would see a new star appearing and disappearing in minutes. An event that occurred when the universe was only 7% of its current age. The energy released by this explosion is equivalent to converting several solar masses into pure energy in seconds. And there are things even more mysterious. The WOW signal is a radio signal recorded in the year 1977 as part of the SETI project. 72 seconds of narrowband radio emission at a frequency of 1420 megahertz, exactly the frequency at which neutral hydrogen emits, the universal frequency that any technological civilization would choose for interstellar communication. The signal was so strong that astronomer Jerry Amon wrote, "Wow," on the printout, coming from the direction of the constellation Sagittarius. He was never registered again, despite dozens of attempts. What was that? A comet that emits hydrogen? An earthly hindrance? Or did we catch a single random flash from an alien civilization transmitting into space? And since then, they have either gone silent or pointed the beam in the other direction. We are looking for alien life everywhere. SETI listens to the sky, hoping to pick up radio transmissions. Astronomers are looking for techno-signatures, signs of alien technology. Dyson spheres that produce excess infrared radiation. Megastructures that outshine stars. Traces of industrial pollution in the atmospheres of exoplanets. For now, there is silence. The Fermi paradox hangs over us like a sword of Damocles. If the universe is teeming with life, where is everyone? Why isn't the sky buzzing with radio broadcasts? Why don't we see traces of a galactic civilization that must have arisen billions of years ago? Maybe life is incredibly rare. Maybe the transition from chemistry to biology requires such a specific set of conditions that it happens only once per galaxy, once in 100 galaxies. Maybe we are alone not only in the Milky Way, but also in a local group in a local supercluster. A lonely island of consciousness in an ocean of dead matter. Or maybe life is ordinary, but reason is rare. Billions of planets may be teeming with bacteria, but only a handful will ever give rise to something capable of questioning its existence. Evolution is not directed toward reason. It is aimed at survival and reproduction. Intelligence is a costly accident that appeared on Earth only once out of billions of species that have existed in 4 billion years. Maybe we're the result of an incredibly unlikely chain of events. Or maybe intelligent civilizations are common, but short-lived. The Great Filter is a hypothetical barrier that destroys technological civilizations soon after they arise. Nuclear war, ecological collapse, artificial intelligence spiraling out of control, synthetic pathogens. The window between the development of technology and self-destruction may be only a few centuries. If true, the cosmos is littered with the ruins of civilizations that reached our level and a little further before disappearing. Or maybe they are there, but they are silent. Dark forest. The universe may be full of predatory civilizations that destroy anyone who reveals their position. In such a cosmos, only those who hide survive. Broadcasting into space is suicide. Every civilization that survives to the interstellar era has learned this lesson. They are hiding, listening, but never communicating. And we, young and naive, scream into the void, not understanding the danger. Or maybe they transcended. Advanced civilizations can lose interest in the physical world, going into virtual realities, uploading their consciousness into computational substrates. Why explore the galaxy when you can create infinite worlds inside? Why communicate with strange biological forms when your existence is pure information processed on quantum computers? Post-biological civilizations may be invisible to us, existing in computational spaces that we cannot detect. But as we search, the universe continues to amaze us with phenomena that seem almost magical. Gravitational waves are ripples in space-time created by catastrophic events. We didn't discover them until 2015, 100 years after Einstein predicted their existence. GW 150914 is the merger of two black holes with a mass of 36 and 29 solar masses. They orbited each other, approaching, accelerating, until they merged into a single black hole, releasing energy equivalent to 3 solar masses in the form of gravitational waves. In the last fraction of a second, they emitted more power than all the stars in the entire observable universe combined. And this energy reached Earth as a slight tremor in space, a change in the distance between the LIGO mirrors by 1,000th of the size of a proton. We are now listening to the gravitational symphony of the cosmos. New mergers are registered every week. Black holes, neutron stars, objects of unknown nature whose mass falls into the gap between the heaviest neutron star and the lightest black hole. Were they hybrids? Quark stars? Something even stranger? GW 170817 is the merger of two neutron stars, which we observe both in gravitational waves and in the electromagnetic spectrum. Kilonova is an explosion that creates heavy elements. Gold, platinum, uranium, most of the heavy elements in your body, in your phone, in the Earth's crust, were created in such cataclysms. We are literally made of stardust, but not just ordinary stars. We are made of explosions, of collapses, of the most violent events in space. The universe is an alchemical factory. The Big Bang created only hydrogen, helium, and traces of lithium. Everything else, the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, was forged inside the stars. Stars are nuclear reactors that slowly convert light elements into heavy ones. When a massive star runs out of fuel, its core collapses and the outer layers explode outward in a supernova, spreading these elements throughout the galaxy. Nebulae are forming. New stars are lit. Planets condense from debris. And on some planets, these atoms are organized into molecules, molecules into cells, cells into organisms, organisms into beings capable of understanding their own history. We are a byproduct of stellar evolution, the way the universe knows itself. Carl Sagan said, "We are the cosmos' way of knowing itself." This is literally true. The atoms in your brain were once in stars. They've gone through nuclear fusion, supernova explosions, interstellar clouds, planet formation, for billion years of evolution. And now, they're organized into a structure capable of speculating about their origins. The probability of this is staggeringly small, but here you are. But the universe doesn't care about you. It did not create conditions specifically for life. We exist in a narrow window of space and time, where the conditions happen to be right. Most of the universe is deadly hostile. Vacuum, radiation, extreme temperatures, black holes, neutron stars, gamma-ray bursts, supernovae, rogue planets hurtling through the darkness at thousands of kilometers per second, comets that can wipe out civilization, asteroids the size of a city, capable of causing a global winter. 66 million years ago, an asteroid with a diameter of 10 kilometers struck the Yucatan Peninsula at a speed of 20 kilometers per second. The energy of the impact is equivalent to 10 billion atomic bombs. The Chicxulub crater is a scar on the face of the Earth, a reminder that planets are vulnerable. The impact threw trillions of tons of dust into the atmosphere, blocking sunlight. Temperatures have dropped. The plants died. Food chains collapsed. 75% of all species became extinct. The dinosaurs, which ruled the planet for 160 million years, disappeared in a few years. Their place was taken by mammals, small, nocturnal creatures that survived the disaster. Without that blow, there would have been no primates. There would be no people. All human history is a byproduct of cosmic accident, and it can happen again. Asteroids and comets are still there, millions of them orbiting the sun in unstable orbits. Most are safe, but some cross the Earth's orbit. Apophis, an asteroid 340 meters in diameter, will pass 31,000 kilometers from the Earth in 2029, closer than geostationary satellites. If the calculations had been a little different, if its orbit had been a little different, it could have collided. The energy of the impact is equivalent to 1,000 megatons. The whole city could have disappeared. A tsunami hundreds of meters high if it fell into the ocean. We scan the sky, catalog near-Earth objects, and plan asteroid deflection missions. DART, a NASA mission, successfully changed the orbit of the asteroid Dimorphos in 2022, crashing into it at a speed of 6 kilometers per second. Proof of concept. We can protect ourselves, but only if we see the threat in advance. A dark comet that came from the Oort cloud could give us only a few months of warning. Too little time to start an interception mission. The universe is vast and indifferent, but it's also the only place where we exist. We are standing on this small rock, the third from an unremarkable star in the quiet suburbs of the Spiral Galaxy, among hundreds of billions of other galaxies. And yet we are able to understand quasars, see the birth of the universe in the CMB, and predict the merger of black holes billions of light years away. We can keep in mind the structure of superclusters, understand quantum mechanics, and decipher the equations that describe the fabric of space-time. But the more we learn, the more questions arise. Each answer opens up 10 new riddles. What is dark energy? What is dark matter made of? What was there before the Big Bang, if there was anything at all? Are there other universes? Is there life somewhere else? Or are we a lonely spark of consciousness in an infinite cosmos? Maybe we'll never know all the answers. Maybe the universe is too big, too complex, too strange to be fully understood by a single species on a single planet. Maybe there are limits to knowledge, horizons beyond which we will never look. Not only cosmological horizons, established by the speed of light and the expansion of space, but also conceptual horizons. Ideas so fundamentally alien to our way of thinking that we can't even formulate the right questions. Or maybe in 1,000 years, in 1,000,000 years, if we survive, if we spread out among the stars, if we keep asking questions, we will understand. We will decipher the mysteries of dark matter and dark energy. We will find signs of other civilizations or understand why there are none. We'll look into the quantum foam of space-time on the Planck scale and see what reality is really made of. We will understand consciousness, life, meaning. We will become a species capable of not only observing the universe, but shaping it, guiding its evolution, leaving a trail that will outlive the stars. But now, at this moment in cosmic history, we're still children taking our first steps. We've just learned how to leave our planet. We've just started detecting planets around other stars. We've just heard gravitational waves. We're on the cusp of incredible discoveries, with telescopes capable of peering into the atmospheres of exoplanets in search of biosignatures, with detectors capable of picking up the faintest whispers of the cosmos, with equations that can link quantum mechanics and gravity into a unified theory of everything. The anomalies we see, the cold spot, the dark stream, the giant structures, the strange signals, are not errors in the matrix. These are hints, breadcrumbs leading to deeper understanding. The universe speaks to us through these anomalies, shows us where our theories are flawed, where we need to dig deeper, think more boldly, and let go of preconceptions. Space does not have to live up to our expectations. It does not have to be understandable. It just is there, wild, strange, huge beyond imagination, full of wonders and horrors, places of unimaginable beauty and unspeakable cruelty. Galaxies colliding in slow motion for billions of years. Stars born in the pillars of creation. Planets where it rains diamonds, where winds blow at the speed of sound, where the temperature is high enough to melt a stone or boil nitrogen. Black holes devouring stars. Neutron stars shooting jets of radiation through galaxies. Quasars shining brighter than 1 trillion suns. And somewhere in this madness is us. Witnesses, observers, storytellers, the only known beings who can look at all of this and ask, why? Perhaps this is our role, not to control the universe, not to conquer it, but to understand. Look into the abyss and do not turn away. Continue to search, explore, discover, even knowing that some mysteries may remain beyond our comprehension. To continue because the alternative, ignorance, is worse. Because every discovery, every answer, even a partial one, brings us closer to something important, towards an understanding of our place in space. To realize how small we are and how incredible we are at the same time. The universe doesn't care if we understand it or not. It will continue to expand. Stars will continue to be born and die. Black holes will continue to merge. Galaxies will continue to dance their ancient dance, with or without us. But as long as we are here, as long as we have eyes to see and minds to understand, we will look into deep space and look for answers to the questions that humanity has been asking since the first man looked up at the night sky and wondered, what is there? And in every anomaly, in every contradiction, in every riddle, there is a promise. The promise that the universe has not yet revealed all its secrets, that there are more wonders ahead, more discoveries, more horizons to cross. The cosmos is calling, and we, despite all our shortcomings, despite our fragility, respond. Because that's what we do. This is who we are, pioneers at the edge of infinity.